Before we get into any formulas today, I want to tell you about something that happened on the morning of August 6th, 1945, in a city called Hiroshima. What I'm about to read is from documented Hibakusha testimony. Hibakusha is the Japanese word for atomic bomb survivor. Everything I'm about to describe comes from real accounts. A girl of 8 is at home. Her mother left earlier that morning, walking toward the center of the city. At 8:15, the world turns white. The blast wave hits seconds later. Windows explode inward. The ceiling comes down. The girl is thrown against a wall and does not remember the next several minutes. When she comes to, the house is still standing, barely. She crawls outside. The sky is the wrong color. There is a sound she has never heard and will never be able to describe. A city making a single sound all at once. She waits. Hours pass. She does not know what has happened. She does not know a bomb was dropped. She waits. Near dusk, something comes to the door. It moves on its hands and knees. Its arms are raised slightly, held out in front of its body, and she will understand later that this is because the skin has burned away and is hanging in long sheets, and the arms have to be held up so the skin does not drag on the ground. There are no eyebrows. The eyes are swollen, almost completely shut. The hair is mostly gone. The face is a surface, a terrain, not a face. She screams. She runs to the back of the house. She is completely certain that what has come to the door is not human. The thing speaks. She cannot understand what it says. She presses herself into the corner. It speaks again, and something about the sound makes her stop. She looks at its wrist. There is a chain with a small pendant, a piece of jewelry she has touched 1,000 times in her life. Sitting at the end of what she now sees is her mother's wrist. Her mother had been 1.2 kilometers from the hypocenter, close enough to be transformed into what walked through the door, far enough to walk home. She died 8 days later. The official death count for Hiroshima on August 6, 1945 is approximately 70,000 people. That number is a point estimate. The point estimate tells you where the center of the story is. It does not tell you the whole story. Because that girl's mother walked away from the blast, she is not in the day one count, and then died 8 days later. And there were tens of thousands of others like her. People who survived the blast and then spent weeks dissolving from the inside. People who developed cancers years later that nobody counted. People who died by their own hands decades later because of what they had seen and become. The true range of what that bomb did to those people in those bodies across those years is not a single number. The confidence interval is the honest version of the story. The point estimate is only where the center happened to land. That's what we're learning today. Not the center. The interval. The problem a confidence interval solves. You've been running hypothesis tests for several weeks now. You collect a sample. You compute a statistic. You compare it to a critical value. You decide whether to reject the null hypothesis. That whole procedure is answering one question: is the effect real, or is it noise? The confidence interval answers a different question. It asks, how precisely do we know the size of the effect? These are not the same question. A study can tell you that an effect is real, statistically significant, p less than 0.05, while telling you almost nothing about how large the effect is or how precisely it's been measured. A study can reach statistical significance and still leave you almost completely in the dark about what you actually found. Here's the thing. When you run a study with n equals 30 and find a mean difference of 8.5 points, that 8.5 is called your point estimate. It is one number, and one number is not an honest summary of what you know, because what you know is not just that the difference was 8.5. What you know is that the difference was 8.5 in this particular sample of these particular 30 people on this particular day. If you had drawn a different 30 people, you would have gotten a somewhat different number. The confidence interval accounts for that. It says the true population value is probably somewhere in this range. And how wide that range is tells you how much or how little you actually know. A narrow confidence interval means your estimate is precise. You have enough data with low enough variability that you can pin down the true value within a small range. A wide confidence interval means your estimate is imprecise. You don't have enough data, or your data is too variable to narrow the true value down. The range is large. You know something, just not very much. Both of these can be statistically significant. Both can be honest. The width is not a flaw. The width is information. The failure to understand this, the habit of treating a point estimate as if it were the whole answer rather than the center of a range, has produced some of the most consequential errors in the history of human decision-making. We'll come back to that. First, we need to build the intuition from the ground up. July 16th, 1945. White Sands, New Mexico. The United States detonates the first nuclear weapon in human history. They call it Trinity. Before the test, the physicists at Los Alamos had to answer a question that had never been answered before in the history of science. How large would this explosion be? This was not a question with a known answer. The theoretical calculations were based on physics that had never been validated at this scale. There were genuine uncertainties in how efficiently the plutonium would fission, in how the implosion would propagate, and how much total energy would be released. The best estimate from the theoretical group was a yield of roughly 20 kilotons of TNT equivalent, but the confidence interval around that estimate was enormous. The range of plausible outcomes the physicists considered ran from what they called a fizzle, where the device would scatter radioactive material without a significant explosion all the way to yield several times the expected value. And at the upper end of that theoretical uncertainty range was something that had never appeared in a scientific confidence interval before or since: the possibility of igniting the atmosphere. Edward Teller had calculated that the bomb's heat might theoretically ignite nitrogen in the atmosphere, producing a self-sustaining fusion reaction that would spread across the entire planet. Most physicists believed this probability was vanishingly small. Hans Bethe had calculated it was essentially zero, but it was not exactly zero. It was within the theoretical range of outcomes. J. Robert Oppenheimer, the scientific director of the project, was troubled enough by this that he consulted repeatedly with Bethe and others in the weeks before the test. The formal conclusion was that atmospheric ignition was negligible, essentially outside any reasonable confidence interval. But the fact that it had to be formally considered and explicitly ruled out, that a group of the most brilliant physicists in the world had to sit down and work through the math on whether they might end all life on Earth, tells you something important about the nature of the uncertainty they were navigating. Enrico Fermi, one of the greatest physicists of the 20th century, the man who had built the first nuclear reactor, ran a side bet among the scientists the night before the test. The bet: would the bomb ignite the atmosphere, and if it did, would it destroy only New Mexico or the entire planet? He also took separate bets on the yield. This was not gallows humor. Not just gallows humor, it was a physicist explicitly operationalizing his probability distribution. Fermi was doing exactly what a confidence interval does: acknowledging the range of plausible outcomes, assigning rough probabilities to different regions of that range, and making his uncertainty visible rather than hiding it behind a point estimate. The actual yield of the Trinity device was approximately 21 kilotons, almost exactly the point estimate. The atmosphere did not ignite. Here's what matters for today's lecture. The fact that the actual yield landed almost exactly on the point estimate does not mean the confidence interval was wrong or unnecessary. A confidence interval is not a prediction that the true value will end up somewhere other than the center. It is an honest statement that the true value could fall anywhere within the range, and you do not know in advance where it will land. Fermi's side bets were not wrong just because the bomb performed as expected. They were right to exist because the uncertainty was real, the range was real, and pretending otherwise would have been dishonest. Reporting only the point estimate, 20 kilotons expected yield, without the interval would have been a false statement of certainty. The physicists at Los Alamos knew this. They did not suppress the range. They calculated it, debated it, argued about it, and made it the basis of their decision about whether to proceed. That is exactly what you're going to learn to do today. Before I give you the formal definition, I want to build the intuition from something you already know. You know that in a normal distribution, approximately 68% of scores fall within one standard deviation of the mean. Picture the normal curve in your mind. The middle chunk, from one standard deviation below the mean to one standard deviation above the mean, contains 68% of all the scores, 34% on the left side of center, 34% on the right side. Now think about the sampling distribution, the distribution of sample means. You know from chapter 5 that the sampling distribution is itself a normal distribution centered on the true population mean with a spread measured by the standard error. The standard error is just the standard deviation of that distribution of means. Because the sampling distribution is normal, the same 68% rule applies to it. 68% of all possible sample means fall within one standard error of the true population mean. In other words, if you drew sample after sample from the same population, 68% out of every 100 of those samples would produce a mean within one standard error of the true population mean. Now flip that logic around. This is the key move, so follow me carefully. If my sample mean is within one standard error of the true population mean 68% of the time, then the interval that stretches one standard error above and one standard error below my sample mean will contain the true population mean approximately 68% of the time. That interval, your sample mean minus one standard error to plus one standard error, is the 68% confidence interval.
I want to put numbers on this using what you just heard, because the opening story wasn't just an illustration, it was a statistical problem that nobody in 1945 knew how to fully measure. So here's what actually happened in Hiroshima in the weeks after the blast. The people who died on August 6th were the easy ones to count. The harder problem, the one that didn't fit neatly into any existing medical framework, was what happened to the people who walked away. Radiation sickness is not like getting shot. There's no wound. You walk away from the blast. You feel shaken, maybe burned, but alive. Then, over the following days, your body begins to come apart from the inside. The bone marrow stops producing blood cells. Your white cell count collapses. Your immune system, which depends on those cells, shuts down. Your gums begin to bleed, then your nose. Then blood appears in your urine, your vomit. Your hair comes out in clumps, not gradually, but in handfuls all at once. Fevers spike to 104, 105 degrees and don't come down. The lining of your intestines begins to shred. You develop open sores in your mouth and throat that make it impossible to eat or drink. Your skin, in places that weren't even directly burned, develops purple hemorrhagic spots, subcutaneous bleeding, because your blood can no longer clot. And then, somewhere between 1 week and 2 months after the blast, depending on how much radiation your body absorbed, you die. Not from the explosion, from your own immune system collapsing in slow motion. Army medical researchers arriving in Hiroshima in the weeks after the bombing were trying to measure this. They recorded deaths per day across a 64-day observation window, starting from the day after the blast and running through the first weeks of October. The question was, what is the true average daily death toll from radiation sickness and blast injuries combined in the population of people who survived the initial explosion? The population standard deviation for daily deaths in comparable mass casualty radiation events was estimated from available data at 48 deaths per day. The sample mean across those 64 days of records was 220 deaths per day. We want to build a 68% confidence interval around that mean. Two things: find the standard error, and then go one standard error in each direction. That's it. Step one is find the standard error. The formula for the standard error, when you know the population standard deviation, so we're not going from a size, this means that we know everybody in the population, is standard error equals, oops, wrote that wrong. Standard error equals sigma divided by the square root of n. Okay, so sigma is 48 in this case, and n is 64 because we're looking to find the number of deaths per day. We have 64 days of records. Okay, so then of course we're going to take the square root of that. So first find the square root of 64. The square root of 64 is 8. Sorry guys, I'm really sick, so if I say something stupid, then just write it in the comments so that I know and I can fix it in a future video. So of course 8 times 8 is 64. Square root of 64 is 8. So now divide sigma by the square root of 8. So we know sigma is 48. The population standard deviation is 48. So how many times does 8 go into 48? That's 6 times. Okay, 6 times 48. 6 times 8 is 48. Okay, so your standard error is 6. Okay, so write that down. Make sure you've got it written down. The standard error equals 6. That number 6 is telling you something important. It's telling you that if you took hundreds of different 64-day observation windows from this kind of event, the mean daily death count would vary by about 6 deaths per day on average from the true population mean. So 6 deaths per day is the natural statistical bounce in the measurement. So some days more people die from the hemorrhaging and the infection, some days fewer. The standard error captures that variation so that we will know the interval around it. How many deaths are you going to expect if you are a rescue organization that's coming in to help set up hospitals for survivors of an atomic bomb blast? That's why we need to know this interval. Are you going to expect 6 extra or 60 extra? If you can do the standard error and find what the typical variation is around that, then you'd be able to develop this interval, and you'd know like what supplies to pack and so on. Gosh, sorry, I can just hear myself rambling because my brain's not thinking straight. So sorry about that, guys. Okay, so step 2 is you're going to build the interval, right? This should be pretty easy to do. It's kind of self-explanatory, but we're going to go through it. We're 68% confident interval. That's exactly one standard error because we're dealing with population samples, okay? In each direction from your sample mean. Your sample mean is 220, right? So if we look at our normal distribution, the mean is 220 deaths is the average per day. And your standard error is 6. So the lower limit is just you take your sample mean and subtract one standard error, 220 minus 6, that's 214. Your lower limit is 214. Your upper limit, start with your sample mean and add one standard error, 220 plus 6, that's 226. Your upper limit is 226. So a 68% confidence interval, 68% confidence interval, we put it in brackets for this, is 214, comma, 226. That's how you write a confidence interval. Okay, so that bracket notation means your lower limit is 214 and your upper limit is 226. So the interpretation for this is you're 68% confident that the true population mean daily death toll from post-blast radiation sickness and injuries falls somewhere between 214 and 226 deaths per day. That would be very useful for the next time a rescue organization has to deal with a radiation blast, okay? So they could estimate the mean in depending on what city or what area gets blasted, and then you would know that it's probably roughly in this interval, 68% confidence in that interval. Okay, so think about what this means for a moment. The official count of 70,000 on day one was a point estimate. This interval, built from the 64 days of record that followed, is the honest statistical answer to what the bomb kept doing after day one. So 220 deaths per day, every day for weeks. People whose names were not in anyone's initial count, dying in houses and hospitals from their bone marrow shutting down, from infections, their bodies couldn't fight anymore, from bleeding that wouldn't stop. Now, let's bring it back to the whole point of learning about confidence intervals. 68% confident is not very confident. Okay? If someone told you there was a 68% chance the bridge you were about to cross wouldn't hold your weight, you would find a different bridge. In research, we need to be much more confident than that, which is why we use 95% and 99% confidence intervals. But the 68% interval is where the logic starts, and it shows you exactly what a confidence interval is doing. We take our sample mean, use the standard error to measure how much uncertainty we have, and build a range around that sample mean that will capture the true population mean a specified percentage of the time. The two endpoints of a confidence interval have a name. They're called the confidence limits. The lower confidence limit here is 214. The upper confidence limit is 226, similar to the vocabulary that we used for ranges, because this is a type of range. It's just specifically for confidence ranges.
Now, 68% confident is not very confident. If someone told you there was a 68% chance the bridge you were about to cross would hold your weight, you would find a different bridge. In research, we need to be much more confident than that, which is why we use 95% and 99% confidence intervals. But the 68% interval is where the logic starts, and it shows you exactly what a confidence interval is doing. We're taking our sample mean, using the standard error to measure how much uncertainty we have, and building a range around that sample mean that will capture the true population mean a specified percentage of the time. The two endpoints of a confidence interval have a name. They're called the confidence limits. The lower confidence limit here is 214. The upper confidence limit is 226. What a confidence interval is and what it is not. Here is the formal definition. A confidence interval is a range of values computed from sample data that, under repeated sampling, would contain the true population parameter a specified percentage of the time. That sentence requires careful unpacking. It contains the most commonly misread definition in introductory statistics. Here is what students write on exams, almost universally. There is a 95% probability that the true population mean falls within this interval. That statement feels right. It sounds like what a confidence interval should mean. It is technically wrong. Let me explain precisely why. Once you have computed a specific confidence interval from your data, once you've done the arithmetic and produced, say, 44.98, 51.02, the true population mean is a fixed number. It does not move. It does not vary. It is either inside 44.98, 51.0, or it is not. There is no probability involved anymore because probability applies to uncertain outcomes. And the question of whether the true mean is inside the specific interval is not uncertain in principle. It has a definite answer. You just don't know what that answer is. Here's an analogy that makes this concrete. You flip a coin and cover it with your hand before looking at it. Before the flip, the probability of heads is 50%. But once the coin has landed and is sitting under your hand, the probability that it is heads is not 50% anymore. It is either heads or it is not. A fixed outcome has occurred. You simply haven't observed it yet. The 50% describe the process that generated the outcome, not the state of the outcome itself. Confidence intervals work the same way. The 95% describes the process that generated your interval, not the state of the specific interval you computed. If you repeated your study hundreds of times and computed a confidence interval each time, 95% of those intervals would contain the true population mean, and 5% would not. Your specific interval is one of those, either one of the 95% that captured the truth, or one of the 5% that did not. You don't know which. The 95% is your confidence in the procedure, not a probability statement about this particular interval. The correct interpretation: I used a procedure that captures the true population mean 95% of the time. This specific interval is the result of that procedure. The incorrect interpretation: there is a 95% probability The true mean is in this interval. The rough interpretation. The range likely to contain the true population mean is not technically precise, but it's useful for building intuition and acceptable for most practical purposes. Just know that when you're asked on an exam to explain precisely what a 95% confidence interval means, the answer is about the procedure, not about this specific interval. The formula. The confidence interval formula is CI equal to sample mean, critical value times standard error. There are three pieces there. The sample mean, that's the center of your interval. The standard error, that's the measure of uncertainty in your data. And the critical value, that's a number that determines how wide you cast your net depending on how confident you want to be. The standard error formula is A equal to standard deviation divided by the square root of n. You've seen the standard error before. It was in the denominator of the t-test. It measures how much the sample mean would be expected to vary across repeated samples of the same size from the same population. A smaller standard error means less variability, which means a narrower confidence interval, which means a more precise estimate. A larger standard error means more variability, which means a wider interval. The margin of error. The product of the critical value and the standard error has a specific name that you need to know. The margin of error. Margin of error equal to critical value times standard error. The margin of error is the distance from the sample mean to each confidence limit. It is the part of the confidence interval. When you read in a news article that a poll found 54% support for a candidate with a margin of error of plus or minus 3 percentage points, that 3 is exactly this calculation, the critical value multiplied by the standard error of the proportion. The full confidence interval is lower limit equal to sample mean minus the margin of error. Upper limit equal to sample mean plus the margin of error. The width of the entire interval is 2 times the margin of error. If the margin of error is 3 points, the interval is 6 points wide. If the margin of error is 7 points, the interval is 14 points wide. That width, the total span of the interval, is the number that tells you how precisely you have estimated the true population parameter. A small margin of error means a precise estimate. A large margin of error means an imprecise one. Write this down. Margin of error equals critical value times standard error. It is half the interval width. It is what the means in every published poll and every research report you will ever read. Z or T. Which critical value do you use? The confidence interval formula is CI equals sample mean plus or minus the critical value times the standard error. There are 2 versions of this formula, and the version you use depends on one single decision. Do you know the population standard deviation, or are you estimating it from your sample? Use Z when you know the population standard deviation. When a problem gives you sigma, the population standard deviation, you use it directly to compute the standard error, and you use Z critical values from the normal distribution. The standard error formula in this case is say equal to sigma divided by the square root of n. For a 95% confidence interval, the Z critical value is 1.96. Here's where that number comes from. If you want to capture the middle 95% of the normal distribution, you need to cut off 2.5% in. The Z-score that marks that boundary, the Z-score that has exactly 2.5% of the distribution above it, is 1.96. So you go 1.96 standard errors above and below the sample mean. For a 99% confidence interval, the Z critical value is 2.58. That cuts off 0.5% in each tail, leaving 99% in the middle. You go 2.58 standard errors above and below the sample mean. Written out fully, 95% CI using Z. Sample mean 1.96 times, sigma divided by square root of n. 99% CI using Z. Sample mean 2.58 times, sigma divided by square root of n. Use T when you are estimating from your sample. In real research, you almost never know sigma. What you have is S, the sample standard deviation. You use S as your estimate of sigma. And when you do that, you use T critical values instead of Z critical values. The standard error formula in this case is S equal to S divided by the square root of n. The T critical value comes from the T table at degrees of freedom equal to n minus 1 at your chosen alpha level, looking in the two-tailed column. Written out fully. 95% CI using T. Sample, Ni, DF. 0.5 two-tailed times S divided by square root of n. 9% CI using T. Sample mean, T, DF. 0.1 two-tailed times S divided by square root of n. Here's why the T critical value is always larger than the corresponding Z critical value. When you estimate sigma from your sample rather than knowing it exactly, you introduce additional uncertainty. Your estimate might be a little too high or a little too low. You don't know which direction the error runs. The t-distribution accounts for that extra uncertainty by having fatter tails than the normal distribution, and fatter tails mean you need to go further out to capture the same percentage of the distribution. Larger critical value times standard error gives you a wider interval, and that wider interval honestly reflects the additional uncertainty that comes from estimating rather than knowing the standard deviation. As sample size grows, your estimate of sigma from S becomes more reliable. The t-distribution becomes less fat-tailed. The t critical value converges toward the corresponding z critical value. With very large samples, n above 100, the difference is negligible in practice. The practical rule. 2 sentences. If the problem gives you sigma, the population standard deviation, use z. The critical values are 1.96 for 95% and 2.58 for 99%. If the problem gives you S, the sample standard deviation, use t, look up the critical value in the t table at df equal to n minus 1. In your Aaron textbook, chapter 5 uses z because it's the conceptually cleaner introduction. The population standard deviation is given, so you can focus on the logic of the interval without worrying about the t table yet. Chapter 7 introduces t. And from that point forward, t-based confidence intervals are the standard for real research problems. The logic is identical in both cases. The only difference is where the standard deviation comes from and which critical value you look up. The 2-step procedure. Every confidence interval calculation you will ever do follows the same 2 steps. I don't care whether you're using z or t, whether the sample size is 10 or 1,000, whether the confidence level is 90% or 99%. 2 steps. Every time. Step 1. Calculate the standard error. If you know sigma, say equal to sigma divided by the square root of n mar. If you are using SE equal to S divided by the square root of n, in both cases you are dividing the standard deviation by the square root of the sample size. Take n, find its square root on your calculator. Divide the standard deviation by that number. The result is the standard error. Step 2. Multiply the standard error by the critical value. Then add and subtract from the sample mean. Lower limit equal to sample, mean minus critical value times standard error. Upper limit equal to sample, mean plus critical value times standard error. Start with your critical value, either 1.96, 2.58, or the t-value from your table. Multiply it by the standard error you just computed. That product is your margin of error. Subtract the margin of error from the sample mean to get the lower limit. Add the margin of error to the sample mean to get the upper limit. Write these 2 steps in your notes right now. They do not change. 2 steps. Every problem. By the summer of 1945, the United States was planning the invasion of the Japanese home islands. The code name was Operation Downfall. The question was, what would this invasion cost? How many people would die on both sides if American forces landed on the beaches of Kyushu in November 1945? To answer that question, military planners were computing a confidence interval, not formally, not using the formulas we're using today, but they were doing the same thing. They were looking at their data, measuring their uncertainty, and trying to honestly represent the range of plausible outcomes rather than a single number. The data they were working from came from 4 years of Pacific combat. To understand why the upper bound of that casualty interval was as large as it was, and why serious, experienced military professionals took that upper bound seriously rather than dismissing it, you have to understand what the data actually showed. There are 3 pieces of that story. And after each one, I'm going to show you the numbers it produced.
Okay, so we've talked a lot about how terrible the nuclear bomb was that they dropped on Japan in World War II and how many people died and the things they died of, and that we're recognizing that it is an awful thing. But we're also going to talk about what motivated the Americans to do it. Why did they feel it was necessary? And so I'm also going to tell you some stories from the Americans' perspective. And in this one, we're going to work through our 2-step procedure using a z-score. So there is a Japanese word, kamikaze. Okay, and the kamikaze are one of the reasons why the Americans were so afraid of the Japanese and why we felt that we wouldn't be able to stop the war unless we dropped an atomic bomb. And I'm going to give you a few more examples of what the Americans were thinking and why. So let me tell you what a kamikaze actually is, what a kamikaze pilot is. By late 1945, near the end of World War II, Japan had lost most of its experienced pilots. The air war over the Pacific had been grinding them down for 3 years, and there was no way to replace them fast enough. American fighter planes, the F-65 Hellcat especially, were faster, better armed, and flown by men with far more training. In a straight dogfight, Japan was losing. So Vice Admiral Takajiro Onishi proposed something different. If the pilots were going to die anyway, why not make their deaths count? Why not load the planes with explosives, aim it at an American ship, and fly it on a one-way mission? That is what kamikaze was. Not a metaphor, not a rhetorical device, a weapon system built around the deliberate death of its own pilots. The name came from the divine winds, kamikaze, that had supposedly destroyed the Mongol fleet attempting to invade Japan in the 13th century. The program was officially called the Tokutai, the Special Attack Corps. The pilots wore white scarves, they wrote farewell letters, they were photographed before their missions, some were given sake to drink, many were teenagers. They were often carried to the planes, they were given just enough fuel for their plane to make it to their target and not to get back, so they were going to die no matter what. The manual told them exactly how to do it. Aim between, the bridge tower and the smokestacks. If you're attacking a ship horizontally, aim above the waterline or at the entrance to the aircraft hangar. Don't aim at the flight deck, aim at the elevators. The manual told them never to close their eyes, not in the final seconds, not as the ship filled their windshield. Keep your eyes open so you don't miss. In the final moment, they were supposed to yell "Hisatsu," certain kill, as loud as they could. Now, here's what they actually did. Between October 1944 and August 1945, approximately 3,800 kamikaze pilots died in these missions. They sank 34 American ships. They damaged 368 more. They killed approximately 4,900 American sailors and wounded nearly 5,000 others. At Okinawa alone, which is an island off the coast of Japan, which we still own, one battle, 82 days, Japan flew 1,900 kamikaze sorties. 36 ships were put out of action just in Okinawa. 368 were damaged. The USS Bunker Hill was hit by 2 kamikaze planes in 30 seconds on May 11th, 1945, and nearly 400 of her crew died. One survivor described watching a kamikaze come in. There was nothing you could do. You could hit it, you could set it on fire, and it still came. It was already dead. We were shooting a missile with a man inside it who had decided the outcome before he took off. And Japan had held thousands more aircraft in reserve, pulled back from conventional combat specifically for the invasion of Japan, which we had to do in order to stop Japan in World War II. The estimate when Operation Downfall was being planned was 5,000 to 10,000 kamikaze sorties in the first days alone. If Okinawa looked like that with 1,900 sorties, the American planners asked themselves, what does an invasion of Japan look like with 10 times as many?
And the island battles confirmed the same pattern on the ground. At Tarawa, in November 1943, 4,500 Japanese defenders produced 3,400 American casualties in 76 hours. Of the 4,500 defenders, 17 were taken prisoner. At Iwo Jima in February 1945, 21,000 Japanese defenders produced 26,000 American casualties. More American casualties than there were defenders were taken prisoner. This was the lower half of the data set the planners were working from, not speculation. Documented operational behavior, consistent across every engagement, showing a military that had calculated the deliberate death of its own trained pilots as a rational weapon system.
By the summer of 1945, the U.S. was planning the invasion of the Japanese home islands. Operation Downfall, 2 phases. Operation Olympic Landing on Kyushu in November 1945 and Operation Coronet Landing on Honshu in March 1946. The planners needed to answer a question that had enormous consequences for the casualty estimates. How long would the battle last? Not just one island, the entire campaign. Each phase of the invasion would be a ground battle of unprecedented scale, and the duration of the battle determined everything downstream. How many men would be killed? How long the kamikaze program would have to operate against the fleet? How many civilians would die under the Japanese military's no-surrender policy? To estimate battle duration, the planners did what statisticians do. They looked at their data. The island-hopping campaign had produced 9 major amphibious battles, each with a documented duration, from landing to the declaration of the island secured. They had a sample, they had a mean, they had a standard deviation. They did not have a known population standard deviation. There was no prior history of this kind of warfare to draw a sigma from. They were working from S, not sigma. That is why this is a T example, not because we chose T for convenience or because it was easier, because the data forced it. You use T when you do not know sigma and must estimate it from your sample rather than your population. The planners in this summer of 1945 did not know sigma. Nobody did. They had 9 data points, and they were trying to project from those 9 data points to something vastly larger and more terrible than any of them. Here are the 9 battles and their documented durations in days from landing to secured. Before we do any math, look at that table. Tarawa, 3 days. Kwajalein, 7 days. Those were 1943, early in the campaign, before Japan had adapted to its defenses, before the island-by-island pattern had fully established itself. Now look at what happens as American forces get closer to Japan. Peleliu, 73 days. Leyte, 66 days. Iwo Jima, 36 days. Okinawa, 82 days. The battles are getting longer, not randomly, not because of bad luck, systematically, because Japan was learning how to make the Americans pay for every meter of ground. They abandoned the strategy of stopping the enemy at the beaches and adopted a strategy of defense in depth, caves, tunnels, fortified ridgelines, designed to protract the battle, to extend the battle, and maximize American casualties per day of fighting. General Rupertus predicted Peleliu would be secured in 4 days. The battle lasted 73. He was not an incompetent general. He was operating from a data set that didn't yet include what Japan had become by the fall of 1944. The planners looking at this table in the summer of 1945 were asking, if we invade Kyushu, an island 36 times larger than Okinawa, defended by a force 20 times larger with 70 million civilians who had been armed and trained to fight, how long does that battle last? The table is your data set. Let's build the confidence interval. Step 1. Calculate the sample mean. Add the 9 durations together. 3 plus 7 plus 24 plus 20 plus 8 plus 73 plus 66 plus, can't fit it, 36 plus 82. Let me put the 36 over here so you can see it. Plus 82 is 319. 319 days, okay, divided by n. 9. 319 divided by 9. 9 goes into 319 35 times. 9 times 35 is 315. With 4 left over, so 4 divided by 9 is 0.44. 319 divided by 9 is 35.44, which we will round to 35.4 days. Your sample mean is 35.4 days, okay? That's the sample mean. Step 2, calculate the standard deviation. You would normally compute this from raw data. For this example, I'm going to give you the results rather than work out all 9 deviations by hand. There is a separate the standard deviation of these 9 battle durations is 30.6 days. Why wouldn't we calculate? So the 9 durations, 3, 7, 24, 28, 73, 66, 36, 82 days. So find each deviation from the mean. Okay, we know the mean is 35.4. So 3 days minus 35.4, 7 minus 35.4, 24 minus the mean, 35.4, and the mean all the way down. Okay? Etc. So for 3, it's negative 32.4, negative 28.4, negative 11.4, and so on. Okay? And then you're going to square each of these, right? To get rid of the negative. So 32.4 squared is 1049.76. 28.4, negative 28.4 squared is 806.56. Negative 11.4 squared is 129.96, and so on. Okay? And then you will sum, you obviously will do these, and then we will sum all of those. Okay? So the sum of all of the squared deviations equals 7,496.24 days. And then divided by, not in because we don't have a population, but in minus 1 because it is a sample. We don't know every battle that ever existed. The total number of battles that we have is 9, so in minus 1 is obviously 8, right? So 7,496.24 divided by 8 equals 937.03. And then we squared it. Now we have to unsquare it by taking the square root. And that is 30.6 days. Okay? So that is the standard deviation, right? Or SD, whichever one you want to do. 30.6 days. Okay? Standard deviation, 30.6 days. And that's telling you something important on its own before we even compute a confidence interval. The standard deviation is almost as large as the mean, right? That means the battles in this data set varied enormously, from 3-day sprints to 82-day slogs. That's not noise, right? That is the distribution of how Japan fought, shifting over time from one kind of battle to another. That's very important information on its own. All right, so back to calculating the confidence interval. Step 3, calculate the standard error. Okay, we've done the standard deviation. Now we need the standard error. So the standard error equals the standard deviation divided by the square root of n, okay, which we already have those numbers. S is the same as SD, right? You could write SD there if you wanted, just so you're not confused. So standard error is 30.6 days over the square root of 9, which is, of course, 3. So 30.6 divided by 3 equals 10.2. The standard error is 10.2 days. And now we need to find the degrees of freedom. Step 4. Find degrees of freedom. So degrees of freedom equals n minus 1, which in our case we have 9 battles, minus 1 equals 8. Okay, that's our little wiggle room. So now you're going to open your t-table, find the row for degrees of freedom equals 8, go across to the column for alpha, 0.05, two-tailed, and the value there, I'll just do it for you, is 2.306. Why can't we use z equals 1.96 instead of t equals 2.306? Because we do not know sigma. We estimated sigma from our sample of 9 battles. So that estimate carries uncertainty, right? 9 battles is not a large data set, and the t distribution accounts for that extra uncertainty by having fatter tails. The fatter tails require a larger critical value, 2.306 instead of 1.96. The interval will be wider as a result. That wider interval is honest. It reflects that what we actually know from 9 data sets. Step 5, calculate the margin of error and build the interval. Okay, so the margin of error, I guess I'll write it that way, equals t times standard error, which we've already found our critical t value is 2.306 times the standard error of 10.2. Okay, so 2 times 10.2 is 20. Okay, so your margin of error is 23.5 days. Okay, so the lower limit is 35.4 minus 23.5 days, and the upper limit is 35.4 plus 23.5 days. Okay, and we can calculate that out as 11.9 days, and this as 58.9 days. So with 95% confidence, we have a range of 11. We know the battles will range from 11.9 days to 58.9 days minimum. Okay, minimum to possibly maximum, although we do note that the battles are getting lengthier and lengthier, so the chances are that the next battle could be even longer than 58.9 days. But you certainly would not think that any battle would take less than 12 days. So we use a procedure that captures the true population mean 95% of the time. So based on these 9 island battles, the true mean duration of a Pacific Island battle was estimated to fall between 12 days and 60 days, basically, at this point. That interval is 47 days wide, okay? Very imprecise. But that's not imprecision in the statistical sense. It's the honest representation of the genuine uncertainty in the data. The battles in this data set range from 3 days to 82 days. 9 data points cannot pin that down to a narrow range. A wide interval is telling you the truth about what planners actually knew, and it would be a warning to planners for the invasions to come, that it's going to be difficult. Right? Now look at where Okinawa sits relative to this interval. We're going to be talking about Okinawa in just a few minutes. The interval is 11.9 to 58.9, right? Okinawa ran 82 days. Okinawa is outside the upper limit. It is not inside the confidence interval. It's not even close to the upper limit. What does it mean when a data point falls outside the confidence interval built for the data set it belongs to? It means that data point is a statistical outlier, an observation that doesn't fit the pattern established by the rest of the data. But Okinawa is not random noise. It's the most recent data point. Okinawa is what Japan looked like when defending territory closest to the home islands. Okinawa falling outside the upper bound of the interval is the data set warning you that the pattern is shifting. The later battles were getting longer. The distribution was moving. The planners understood this. They knew the confidence interval built from the full data set was probably optimistic because the early battles at Tarawa and Kwajalein, they were pulling the mean down, and those battles were nothing like what was coming. If you built the interval from only the last 4 battles, Peleliu, Leyte, Iwo Jima, Okinawa, the mean would be 64 days, and the interval would be centered much higher. And the home islands were not one island. They were a campaign across multiple massive islands against a defending force and civilian population larger than anything they'd faced yet in the dataset. So the confidence interval said somewhere between 12 and 59 days per battle phase based on 9 prior battles. Okinawa said the interval is already wrong. The home island invasion would break this confidence interval entirely. That is what the planners were working with. Not a point estimate, not certainty, a range that was honest about what the data supported, and a most recent data point that was already outside the range, pointing towards something worse.
The Cave at Chibichirigama, April 1945. The Americans have landed on Okinawa. The battle is 3 weeks old. In the northern part of the island, in a limestone cave called Chibichirigama, a group of civilians has taken shelter. Mostly women, elderly men, children. The Japanese military had spent months telling the civilian population of Okinawa what to expect from the Americans, specifically, deliberately, systematically. The messaging was this: American soldiers will rape the women. They will torture the men. They will kill the children. Death is preferable to capture. Surrender is disgrace. If you must choose between death and the Americans, choose death. American soldiers approach the cave. They have a Japanese-speaking interpreter with them. They call into the entrance. They promise safety. They promise food. They set supplies down at the mouth of the cave as evidence. They are genuinely trying. The people inside the cave can hear them. 85 people were sheltering in Chibichirigama. Keen came out. The rest died inside. Post-war survivor testimony documents what happened. In the darkness, families decided together that they would not surrender. The methods varied: fire, hand grenades that Japanese soldiers had distributed to civilian populations specifically for this purpose, strangulation, drowning in the water pooled at the back of the cave. Mothers went first with their children. Then others helped each other, or did it themselves. The American soldiers outside did not know what was happening. The interpreter kept calling. They left the food. 67 people died in a limestone cave, while American soldiers stood outside promising them sandwiches. Chibichirigama was not a unique event. It was documented because it was investigated after the war. Similar events occurred across the southern part of the island as the battle compressed the civilian population toward the coast. Here is what Okinawa looked like as a data point. American dead, 12,520. American wounded, 38,000. A 35% casualty rate among committed American ground forces. Japanese military dead, approximately 110,000 out of 117,000 defenders. Japanese civilian dead, approximately 100,000, between 1/4 and 1/3 of the entire pre-battle civilian population of the island. Many were killed by Japanese military forces who executed civilians rather than allow surrender, or forced them into combat. A substantial number died the way the people in that cave died. Now scale that to the home islands. Not one island with 117,000 defenders and a civilian population in the hundreds of thousands. A defending force roughly 20 times the size of Okinawa. A civilian population of 70 million who had been subjected to the same messaging as Okinawa for longer, more intensively at the national level. The Ketsugo Defense Plan explicitly incorporated those 70 million civilians into the defense. The government had distributed bamboo spears to civilian women and children, not as a symbol, as weapons. Those 5,000 to 10,000 kamikaze sorties were waiting. The island pattern, fight until there's almost no one left, was the only pattern the data showed. The historical pattern, Nanjing. December 1936, 8 years before the invasion estimates were written, the Japanese military entered Nanjing, the capital of the Republic of China. What followed over the next 6 weeks is one of the most thoroughly documented atrocities of the 20th century. Documented in real time, not by post-war prosecutors, but by the Japanese soldiers themselves, by the neutral Western business people and missionaries who stayed behind, and by photographers whose images were suppressed for years afterward. The Japanese command structure did not lose control of its soldiers. It made decisions. Officers organized what happened systematically. Chinese male civilians were bound together with wire. and marched to the banks of the Yangtze River in groups of hundreds. Machine guns were set up. The river ran discolored for days. Chinese prisoners of war were used for bayonet practice, not in the heat of combat, but as organized training exercises with officers observing. A Japanese newspaper, the Tokyo Nichi Shimbun, ran a story about a competition between two officers to see who could kill 100 Chinese prisoners first using a sword. The newspaper printed their names. It printed their running totals. It reported the final score when one officer reached 100 first, then updated readers when the other reached the same number, and noted that both men had raised the target to 150. This ran as if it were a sports score. It was read over breakfast. The women of Nanjing. An estimated 20,000 to 80,000 women were assaulted over those 6 weeks. The range is that wide because of how much evidence was destroyed. The violence was systematic enough that Western witnesses, business people, and missionaries with no political stake in the outcome documented it in diaries and formal letters of complaint to the Japanese embassy. Those letters produced almost no response. Minnie Vautrin was the dean of Jinling Women's College, an American missionary educator who had spent 20 years in China and refused to leave when the Japanese arrived. She turned the college into a refugee camp. At its height, she was sheltering approximately 10,000 women and children on a campus built for a few hundred. She stood at the gate physically blocking soldiers who came demanding women. Her being American gave her a few inches of authority she had no legal right to under international law, and she used every inch of it. Her diary is one of the most important primary documents from those weeks. December 16, 1937. I know not what the night may bring forth. God protect them. She stayed for years. When she finally left, she had a complete mental breakdown on the voyage home. She never recovered. She died by suicide in 1941, 4 years after Nanjing, in a world where the war was still going. She is one more death in the interval, arriving late, the way so many deaths do. Total dead at Nanjing between 100,000 and 300,000 over 6 weeks. The width of that interval is itself a historical crime. It is what 8 decades of evidence destruction and official denial produces. But the number, whatever it precisely was, established something the planners in 1945 could not ignore. This military had demonstrated in a controlled city against a disarmed civilian population, under no military necessity, what it was capable of when it had no external check on its conduct. So here, now, is the full data set. Tarawa, 17 prisoners out of 4,500 defenders. Iwo Jima, 216 prisoners out of 21,000. Okinawa, a 35% American casualty rate. 110,000 Japanese military dead, 100,000 Japanese civilians dead. 3,800 kamikaze missions across the war, 5,000 to 10,000 held in reserve for the invasion. 70 million civilians armed and prepared for resistance under Ketsugo. And behind all of that, Nanjing, 8 years of documentation showing what this military had done when it believed it was unconstrained.
So now imagine you're the leaders deciding whether to invade Japan or not. Let's build a confidence interval around American casualties and what we could expect. So we have 9 battles, the same 9 battles we just used to look at the duration of battles. And here is the data for actual casualties. At Chihuahua, 18,000 Marines landed and approximately 3,300 were killed or wounded. That's an 18% casualty rate. At Kwajalein, 41,000 landed and with 1,900 casualties, not too bad, 5%. At Saipan, 71,000 troops with 16,612 casualties, 23%. At Guam, 55,000 troops landed, 7,800 casualties, that's 14%. At Tinian, 50,000 troops, approximately 2,000 casualties, 44%. At Peleliu, and this is the highest casualty rate of any American amphibious operation in the war, 28,000 troops, 9,800 casualties, 35%. At Leyte, 200,000 troops, 15,000 casualties, 8%. Iwo Jima, 75,000 troops, 26,821 casualties, that's 36%. At Okinawa, 183,000 troops landed, 49,151 casualties, that is 27%. Okay, before we do any math, look at those rates across time. Chihuahua, 18%, Kwajalein, 5%, Tinian, 4%. Those are the early battles, 1943, early 1944. Then look at what happens. Peleliu, 35%, Iwo Jima, 36%, Okinawa, 27%. The rates are going up, not randomly, because Japan is learning how to make Americans pay more for every island. The same pattern we saw in battle duration, the same trend pointing in the same direction. The planners in the summer of 1945 knew this. They were looking at exactly this table and asking, if we land on Kwaishu, if we invade Japan, what percentage of our men will become casualties? The confidence interval is the best honest answer to that question. So let's calculate it. Step 1, we need to calculate the sample mean. So add the 9 casualty rates together for all 9 battles. You have 18 plus 5 plus 23 plus 14 plus 4 plus 35 plus 8 plus 36 plus 27. Okay, add all those together, and the sum is 170 percentage points divided by 9 battles. You have your average, your sample mean of a casualty rate of 18.9%. Okay, that is the mean. Step 2 is calculate the standard deviation. Okay, I'm going to give you the results here and not calculate everything because that's a lot of work, but do pause it and do it yourself. Okay, it's exactly the kind of practice problems that you guys need to be doing. Okay, so again, to do the standard deviation, you're going to take each data point and subtract the mean, which is 18.9%. Okay, so 18 minus 18.9% would be minus 0.9%. Okay, and then you just do that all the way down. So the standard deviation. Oh, and then obviously square it, sum it, square root it. Okay. And then, so the standard deviation in this case, just to hurry us along, would equal out to 12.2 percentage points. That's how much each of these battles deviated from the average. Okay, so the mean is 18.9. The standard deviation is nearly as large as the mean. That tells you that these rates varied enormously from 4% at Tinian to 36% at Iwo Jima. Okay, that's the actual range of what it costs to take a Pacific island from Japan, depending on the island, the defenders, the terrain, the year, etc. All right, step 3. We're going to calculate now the standard error. Okay, so standard error is the standard deviation divided by the square root of n. So in this case, our standard deviation is 12.2% divided by the square root of how many battles we had, which is 9. The square root of 9 is 3, so 12.26 divided by 3. Let's see, goes into 12 4 times exactly. So your standard error is 4.07 percentage points. Okay, standard error 4.07 percentage points. Now, let's just write standard error is 4.07 percentage points. Our n is equal to 9. Our mu was, I'm just writing this down just so it's easily 2.9%. Okay. So find the degrees of freedom is step 4. Okay, degrees of freedom. So degrees of freedom equals n minus 1. Okay, very simple. So we have 9 battles minus 1. Our degrees of freedom equals 8. Okay, so we go to our T table. Okay, degrees of freedom equals 8. We're going to do an alpha of, our alpha of 0.05, and we'll do a two-tailed t-test. So the t equals 2.306. Now for the hypothesis test, we obviously would be doing one tail, but for confidence interval itself, two tail is correct, okay, because you're looking for the two ends of our confidence distribution, so to speak. So same critical value as the battle duration example, same degrees of freedom, right? That's not a coincidence. It's the same 9 battles. The data set is the same, only the variable changed. So now we're on to step 5. Calculate the margin of error, okay? Margin of error, and then build the interval. So the margin of error is your t, your critical t value, times your standard error, and that is, of course, 2.306 times our standard error of 0.07%, okay? So 2 times 4.07 is 8.14, 0.3 times, let me think this through. Okay, so approximately 9.4%. So your margin of error is approximately 9.4 percentage points, okay? And then build the interval. So your mean, right, is 18.9%, 18.9%. So we're going, our margin of error is how much on this side, how much on that side, and altogether we call that the confidence interval. So minus 9.4 and plus 9.4. Okay, and then we get our entire interval, and we write that out by, we're saying we're 95% confident, have a 95% confident interval, that death rates will be minimum of 9.5%, and we don't do a dash, we do a comma, and on the high side, 28.3%, with recognition that these numbers, just like the battle, that this one is getting higher. So casualty rates will probably be on the closer end of 28.3%, if not larger. Okay, so that captures the true population mean 95% of the time. based on these 9 island battles. The true mean American casualty rate for Pacific island operations is going to fall between 9.5% and 28.3%. So the interval is 18.8 percentage points wide, and it's wide because 9 battles can't pin down a rate any smaller than that when the casualty rates are ranging from 4% to 36%. Okay, it's wide because the distribution again was shifting and getting larger as the war progressed. So this interval is honest, but any report would have to say that we've already had battles with casualty rates over this one, so the confidence interval is shifting. Okay. And of course, that's why it's only 95% confident, because there's still in that 5% leftovers, there's a good chance that it's going to go, not a good chance, there's a 5% chance that it's going to go outside of this interval at this current moment. Okay, it's recognizing that even at 95%, we're not totally confident. So if we look at the planned operations, Operation Olympic, which was the first phase of the home island invasion landing on Kyushu in November of 1945, had a planned committed ground force of approximately 767,000 men. If you take just the lower bound of our interval, the 9.5% of 767,000, okay, 767,000 times 0.095 it's approximately 75,000 American casualties, okay, in the first phase alone. If you look at the upper bound, recognizing that there's a good likelihood it'll even be higher than that, 28% of 767,000 men is 217,000 American casualties just in that first phase. Okay, that's not the full invasion. That's phase 1. Operation Coronet for the Honshu landing. Tokyo's island, scheduled for March of 1946, had a planned additional 1.171 thousand troops, so 1,171,000 troops. Applying the same interval on the upper bound of 28.3%, which is still very conservative, you're talking another 331,000 dead. Okay, so the combined range with conservative estimates is 184,000 to 548,000 just starting the invasion of the Japanese islands, not even getting to Japan. Now look at where Okinawa sits in that casualty rate data set, 27%. That's inside the interval, but look at the trend again. Pelelu, 35%, Iwo Jima, 36%, Okinawa, 27%. Those 3 late battles averaged 32.7%, which is near the upper end of the interval. The early battles are pulling the mean down to 18.9%. If you built this interval only from Pelelu, late Iwo Jima, and Okinawa, the 4 battles immediately preceding the planned invasion, the mean casualty rate would be 26.5%, and the confidence interval would shift dramatically upwards. The planners knew this. The confidence interval was built from the honest full data set. The honest full data set was probably optimistic about how many Americans would die. And the home islands were not Okinawa. Kyushu had 900,000 defenders. Okinawa only had 117,000. The defending force was nearly 8 times larger. The civilian population had been armed and organized under Ketsugo. The kamikaze program had 5,000 to 10,000 sorties waiting, airplanes waiting to crash themselves. Everything that made Okinawa's 27% casualty rate what it was, every cave, every civilian armed with a bamboo spear, every pilot who kept his eyes open until the ship filled his windshield, was waiting on Kyushu multiplied by 8. The confidence interval gave the planners a range. The range was honest, and everything they knew told them the true value was going to land at the high end of it or above it entirely. That is what a confidence interval is for, not to give a false sense of certainty, to give an honest statement of what the data supports and to show you exactly where the edges of what you know begin to crumble.
The Joint Chiefs Planning documents for Operation Downfall produced casualty estimates that reflected this data set honestly. The low estimate from General MacArthur's staff, approximately 50,000 American dead. The high estimate from the Secretary of War's office, over 1 million American dead, derived by scaling Okinawa casualty rates to the size of the Japanese home islands and the defending force. Admiral Leahy's estimate was 250,000 dead. General Marshall's working figure was 250,000 to 500,000. The War Department ordered 500,000 Purple Heart medals in anticipation of the invasion. That stockpile was so large that Purple Hearts awarded in every American conflict since 1945, Korea, Vietnam, the Gulf War, Iraq, Afghanistan, have been drawn from it. As of the time this lecture was written, it has still not been exhausted. The confidence interval around American invasion casualties was approximately 50,000 1 million. The point estimate most planners worked from was approximately 250,000 American dead. Japanese casualties, military and civilian, were estimated even more uncertainly. Scaled from Okinawa, where Japanese military and civilian dead together approached the entire pre-battle population of the island, the confidence interval around total Japanese casualties included values in the millions.
Now, let's look at how many people would die from the bomb being dropped in order to stop these casualties.
A team of physicists runs 25 theoretical yield calculations, varying the inputs within their range of uncertainty, slightly different assumptions about fission efficiency, slightly different assumptions about implosion geometry. The mean predicted yield across those 25 calculations is 19.8 kilotons. The standard deviation across the calculations is 6.2 kilotons. Construct a 95% confidence interval around this mean estimate. We do not know the population standard deviation here. We have S, the standard deviation computed from these 25 calculations. So we use T. 4 steps. Step 1, calculate the standard error. Equal to S divided by the square root of N. S is 6.2. N is 25. Find the square root of 25. The square root of 25 is 5. Your standard error is 1.24 kilotons. SA equals 1.24. Step 2, find the degrees of freedom. DF equal to N minus 1 equal to 25 minus 1 equal to 24. Your degrees of freedom are 24. Step 3, find the T critical value. Open your T table, go down the degrees of freedom column until you reach 24. Go across to the column for alpha equals 0.5 two-tailed. The value there is 2.064. T equals 2.064. Notice 2.064 is larger than 1.96, the Z critical value for 95% confidence. That difference is the extra uncertainty from estimating sigma from only 25% calculations. The smaller the sample, the larger the T critical value, and the wider the resulting interval. That's not a problem, it's the interval being honest about how much you don't know. Step 4, calculate the margin of error and build the interval. Margin of error equal to T times, say equal to 2.064 times 1.24. That's approximately 2.5. Your margin of error is 2.56 kilotons. Lower limit, 19.8 minus 2.56. That is 17.24. Upper limit, 19.8 plus 2.56. That is 22.36. 95% CI, 17.24, 22.36. Interpretation, I used a procedure that captures the true mean prediction 95% of the time. The true mean predicted yield is estimated to fall between 17.24 and 22.36 kilotons. The actual yield of the Trinity device was 21 kilotons. That falls comfortably within this interval. The interval worked. Now notice what the interval tells you that the point estimate does not. The point estimate is 19.8. The interval says the true mean could plausibly be anywhere from 17.24 to 22.36, a range of about 5 kilotons. At the scale of nuclear weapons, a 17 kiloton device and a 22 kiloton device produce substantially different blast radii and casualty estimates. The point estimate standing alone suggests a precision that doesn't exist. The interval tells you the truth about what you know. Now, let's compare with the 99% confidence interval. 99% CI from the same data. At DF equal to 24, alpha equal to 0.1, two-tailed, T equal to 2.797. Margin of error equal to 2.797 times 1.24, is approximately 3.47. Lower limit, 19.8 minus 3.47 is 16.33. Upper limit, 19.8 plus 3.47 is 23.27. 9% CI, 16.33, 23.27. The 99% interval is wider, 16.33, 23.27, compared to 17.24, 22.36. For the 95% interval, this is always true. Higher confidence requires a wider interval. You cannot simultaneously be more confident and more precise without collecting more data. The only way to narrow the interval while maintaining the same confidence level is to increase N, which reduces the standard error, which reduces the margin of error. There is no workaround. The atomic bombs killed between 130,000 and 226,000 people across both cities. The confidence interval around invasion casualties, American plus Japanese combined, had a lower bound comparable to the atomic bomb deaths and an upper bound far exceeding them. That upper bound was not paranoid speculation. It was a rational extrapolation from the data. From Ichitsu Hayashi's letters, from the cave at Chibutirigama, from the Tokyo Nichi Shimbun keeping score. Here's the statistical point the historical example is making. When you have two options, Invasion versus atomic weapons, and both options have wide confidence intervals that overlap in their lower ranges but diverge catastrophically in their upper ranges. The decision is not about which point estimate is lower. It is about what the full distribution of plausible outcomes looks like for each option. The point estimate for atomic bomb casualties was approximately 150,000. The point estimate for invasion casualties was approximately 250,000 American dead alone, with total casualties much higher. On the basis of point estimates alone, the decision looks clear, but the confidence intervals change the picture. The lower bound of the invasion estimate overlaps with scenarios where the bombs might have been avoidable. The upper bound, 1 million American dead, plus millions of Japanese casualties, is far outside anything the atomic bombs could produce. When the confidence interval around one option includes catastrophic upper bounds that the other option's upper bound does not reach, decision makers rationally weight those upper bounds. Not just the centers, the full range. This is not irrational pessimism. This is what honest reasoning under uncertainty looks like. Historians still debate whether the bombs were necessary. What the confidence interval framework shows is that the decision was made under genuine uncertainty, with the information available in August 1945, not with the benefit of hindsight, and the uncertainty ranges the planners were navigating were wide enough and dark enough that no option was obviously right or obviously wrong. Acting on honest uncertainty ranges is what the decision actually involved, not on point estimates. After the war ended, the United States Strategic Bombing Survey published a report containing a finding that has been cited for 75 years. Japan would have surrendered by November 1945 without the atomic bombs and without an American invasion. That finding has been treated ever since as a settled point estimate, a definitive answer. The confidence interval around it is enormous. The survey was conducted by an organization with institutional interests in demonstrating the effectiveness of air power. It was based on post-war interviews with Japanese officials who had every incentive to minimize the role of the bombs in their surrender, because acknowledging that the bombs ended the war would mean acknowledging that the military leadership had failed to protect the country, and the Japanese government's own internal records, declassified decades later, show a leadership so divided that even after both bombs had fallen and the Soviet Union had entered the war, the emperor's personal intervention was required to break the deadlock. The foreign minister and the war minister were still arguing. The outcome was not inevitable. It was close and contested. The USSBS finding is not wrong as a possibility. Surrender by November without invasion is within the range of plausible outcomes. It is inside the confidence interval. But it is not the only value in that range. And presenting it as a settled conclusion rather than as one estimate within a wide and contested interval has distorted the historical argument for 3 generations. This is the same error the replication crisis exposed in psychology. A study finds D equals 0.50 P equals rho 3 from N equals 40. The finding is published. It gets cited. It gets replicated in textbooks. It gets taught in courses. The 95% confidence interval around D equals 0.50 from N equals 40 is approximately 0.05, 0.95. That is a 90-point wide range. It includes effects too small to matter clinically and effects large enough to see with the naked eye. The point estimate of 0.50 is one plausible value inside that range. Treating it as the answer is the same error. Report the center, ignore the interval, repeat the center until it hardens into certainty. The honest answer is always the interval. The point estimate is only where the center happened to be. The single most important interpretive point about confidence intervals, and the one most introductory courses underemphasize, is this. The width of the interval is as important as its location. A narrow confidence interval means your estimate is precise. You have enough data with low enough variability that you can pin down the true value within a small range. A mean of 50 with a 95% CI of 48.5, 51.5 tells you the true value is somewhere in a 3-point range. That is useful. You can act on that. A wide confidence interval means your estimate is imprecise. A mean of 50 with a 95% CI of 2278 tells you almost nothing beyond the fact that the true value is probably somewhere between 22 and 78. A 56-point interval is nearly uninformative. You cannot act on that with any confidence. Both of these can be statistically significant. Significance tells you the effect is real, that the interval does not include the null value. It does not tell you the effect is precisely measured. The width tells you 3 things that the center cannot. First, whether your sample size was adequate. A wide interval from a small sample means you need more data before acting on the estimate. A narrow interval from a large sample means the estimate is reliable enough to use. Second, whether 2 studies are actually in disagreement. 2 studies that both find significant effects in the same direction with overlapping confidence intervals are not in conflict. They are consistent with each other even if their point estimates differ. 2 studies whose confidence intervals do not overlap are in genuine disagreement. and that disagreement demands explanation. The Hubble tension in physics, two groups of physicists measuring the expansion rate of the universe with non-overlapping confidence intervals, is a genuine unresolved scientific problem, not a rounding difference, precisely because the intervals don't include each other. Whether the effect is large enough to matter in practice. A confidence interval that is entirely above a meaningful clinical threshold tells you the effect is not just real, but practically significant. A confidence interval that straddles zero, including both positive and negative values, tells you the effect might go in either direction, regardless of what the point estimate looks like. 3 factors determine how wide your confidence interval is. If you want to influence the width to make your interval narrower and your estimate more precise, you need to understand all 3. Factor 1. Sample size. The standard error formula is standard deviation divided by the square root of n. As n increases, the square root of n increases, the denominator of that fraction gets larger, and the standard error, which is the fraction, gets smaller. A smaller standard error means a narrower interval. This is the most direct lever you have for controlling precision. You cannot always reduce the variability in your data. You cannot always change your confidence level. But you can, within the limits of your resources, increase your sample size. There is an important catch, however. Because of the square root relationship, you need to quadruple the sample size to have the interval width, not double it. Quadruple it. Doubling your sample size only cuts the interval width by a factor of the square root of 2, which is about 1.41. That's a 29% reduction. Meaningful, but not dramatic. To cut the interval width in half, you need 4 times as many participants. This is one reason large studies are expensive and why the precision gains from adding participants diminish fast. Factor 2. Variability in the data. The standard error is also proportional to S, the standard deviation of your data. More variable data produces wider intervals. Less variable data produces narrower intervals. If people in your sample are all very similar to each other, your standard deviation is small and your interval is narrow. If they vary widely, your standard deviation is large and your interval is wide. This factor is often outside your control. You cannot reduce natural variability in your population, but you can anticipate it in study design. If you know a variable is highly variable, you know you'll need a larger sample to get a precise estimate. Factor 3. Confidence level. A 99% confidence interval is wider than a 95% confidence interval from exactly the same data. To capture the true value more often, to cast a net that catches the target 99 times in 100% rather than 9900, you have to cast a wider net. The critical value for 99% confidence is 2.58 compared to 1.96 for 95% confidence. That larger critical value multiplied by the standard error, which gives you a wider interval. The implication: you cannot increase confidence and decrease width at the same time without collecting more data. These are not independent choices. If you want a 99% interval that is as narrow as your 95% interval, you need a larger sample. The relationship between confidence, precision, and sample size is not negotiable. Quadrupling the sample size halves the interval width. Let me show you rather than just assert it. Same study, same sample mean, same standard deviation. The only thing that changes is the sample size. Version 1. N equal to 25. Naval historians studying operational records from American destroyers that served in the Okinawa campaign. They record the number of days each destroyer was at sea during the campaign before requiring a port call for mechanical maintenance. A first sample of 25 destroyers produces a mean of 67.4 days at sea with a standard deviation of 12.3 days. We want a 95%. Step 1. Standard error. Equal to S divided by the square root of n equal to 12.3 divided by the square root of 25. Square root of 25 is 5. So 12.3 divided by 5. To divide 12.3 by 5 goes into 12 twice with 2 left over. 2.3 divided by 5 is 0.46. So 12.3 divided by 5 is 2.46. SE equals 2.46. Step 2. Critical value and margin of error. DF equal to 25 minus 1 equal to 24. From the t table at df equal to 24, alpha equal to 0.5, two-tailed, t equal 2.064. Margin of error equal to 2.064 times 2.46. 2 times 2.46 is 4.92. 0.06 times 2.46 is 0.1476. 0.004 times 2.46 is 0.146. Is 0.1476 plus 0.1476 plus margin of error equal to 5.08 days. Lower limit, 67.4 minus 5.08 equal to 62.32. Upper limit, 67.4 plus 5.08 equal to 72.48. 95% CI, 62.32, 72.48. Width of interval, 72.48 minus 62.32 equal to 10.16 days. Version 2, n equal to 100. Same mean of 67.4 days. Same standard deviation of 12.3 days. Now the historians expand their record search and find n equal to 100 destroyers. Step 1. Standard error equal to 12.3 divided by the square root of 100. Square root of 100 is 10. So 12.3 divided by 10% equal to 1.23 equals 1.23. Stop and look at what just happened. The sample size went from 25 to 100, it quadrupled. The denominator in the standard error formula went from the square root of 25, which is 5, to the square root of 100, which is 10. The denominator doubled. So the standard error was cut exactly in half from 2.46 to 1.23. This is the square root relationship at work. Quadruple the sample size, double the square root, cut the standard error in half. Step 2. Critical value and margin of error. df equal to 100 minus 1 equal to 99. From the t-table at df equal to 99, alpha equal to 05, two-tailed, t approximately equals 1.984. Notice t value than the 1 for n equal to 25. At df equal to 24, t was 2.064. At df equal to 99, t was 2.984. The t critical value approaches the z critical value of 1.96. This is the fat tails getting thinner effect. The larger the sample, the less extra uncertainty from estimating sigma, and the closer t gets to z. Margin of error equal to 1.984 times 1.23. 1 times 1.23 is 1.23. 0.9 times 1.23 is 1.17. 0.08. 1.23 is 1.0984. 8 times 1.23 is 0.23 is 1.23 is 1.23 plus 1.107 is 2.107 is approximate margin of error equal to 2.44 days. Lower limit. 67.4 minus 2.44 equal to 64.96. Upper limit. 67.4 plus 2.44 equal to 69.84. 95% CI. 64.96, 69.84. Width of interval. 69.84 minus 64.96 equal to 4.8 to 25% equal to 100. Standard error 0.46, 1.23. Margin of error 5.08.44. Interval 10.1, 6 days, 4.88 days. The sample size went from 25 to 100, a factor of 4. The interval width went from 10.16 to 4.88, cut approximately in half. This is not a coincidence. It follows directly from the square root in the denominator of the standard error formula. To have the standard error, you need to double the square root of n. To double the square root of n, you need to quadruple n itself. The practical implication is important for research design. Doubling your sample size, going from 25 to 50, for example, reduces your interval width by a factor of the square root of 2, which is about 1.41. That's a 29% reduction. Significant, but you may not feel it. To get a truly precise estimate, you need substantially larger samples than intuition suggests. This is one reason large studies are expensive, and one reason the precision gains from adding participants follow a curve that flattens out fast. Confidence intervals and hypothesis tests use the same information: sample mean, standard deviation, sample size, and a critical value, and they answer related but distinct questions. A hypothesis test asks, is the effect real? Is the sample mean far enough from the null hypothesis value that I can reject the null? A confidence interval asks, where is the true value? What range of population parameters is consistent with what I observe? The connection is direct, and the rule is simple. If the null hypothesis mean falls outside the confidence interval, reject the null. If it falls inside, retain the null.
Let me apply this to the island battle duration example. We computed a 95% confidence interval of 11.9 and 58.9 days long. The pre-war military planning assumption, based on early Pacific operations before the island hopping campaign, was that island battles would average approximately 5 days. That 5 is the null hypothesis value. Is 5 inside the interval 11.9 to 58.9? Obviously not. 5 is below the lower limit of 11.9. It is outside the interval. Therefore, we reject the null hypothesis at alpha of 0.05. The island hopping campaign took significantly longer per battle than pre-war planning assumed, not because the data is noisy and that there's a lot of variation, but because Japan changed how it fought. The early victories at Tarawa and Kwajalein created an expectation that never held true again. Now, here's the thing. The confidence interval gives you more information than the hypothesis test alone, and I want to show you exactly why. Suppose two studies both find non-significant results. Both fail to reject the null. In a hypothesis test, those two results look identical, non-significant, done. But what if the first study produced a 95% confidence interval of 52.2 to 53.8, and the null is 53? The entire interval clusters very close to the null value. The effect, if there is one, is probably tiny. That's genuinely uninformative about whether something real is happening. Now, suppose the second study produced a 95% confidence interval of 47.5 to 58.5, and the null is also 53. That interval is wide, 11 points wide, and it includes values both well below and well above the null. The study is genuinely inconclusive. You can't distinguish a null effect from a substantial effect with this data. That's a very different kind of non-significance. Both are non-significant. Only the confidence interval tells you which situation you're actually in. The p-value tells you whether to reject. The interval tells you what you actually found and how precisely you found it. So always report the confidence interval alongside the p-value, always.